Okay, so hi everyone. I'm Yaron from Iguazio, founder and CTO. We're going to speak today about how to bring data science to life faster using machine learning operations, MLOps, and various automation tools. Let me also open up the video. And with that, let's start. So before we go into the technical details, let's understand the challenges and what we need to solve. So the first thing that we see is that the world is moving from essentially more of a batch analysis and even interactive analysis with the dashboard and BI and analytic tools to solving problem using machine learning, essentially machines that interpret event and react to them, whether it's Facebook or Google or people that build recommendation engines and automated fraud and detection and predictive maintenance, essentially machines that react to events but using AI. So they're trying to do it really, really fast and also with as much data as they can in order to bring value to the business. So essentially everyone is moving from this reactive approach to a more reactive approach and applying machine learning and AI to real business value, and that brings some challenges with it. So usually today when you think about machine learning and data engineering, data analytics, so machine learning is really more in the research environment. So there are systems where people bring data usually in data science starts small, CSV files, Excel spreadsheets. You throw it into notebooks and you're starting to massage the data, try to figure out where is there a pattern, and then running sort of training and building models and using those models to build applications. In some cases, those are simple reporting applications that could predict that, you know, if last month we did certain things, maybe next month we could do them differently. But as the applications evolve and we're trying to deploy those applications in production, we see that we have production pipelines. Those production pipelines is where we integrate our machine learning with the real world. The real world meaning operational databases that we need to bring data from using ETL processes, streaming data, you know, transactions, location updates, all sorts of real data that flows into the system and has to be incorporated in our decisions. As the data, when the data is more fresh, we can make more accurate decisions. And also APIs. Today in the world, a lot of the data is served through APIs. Information about customers, information about weather, about traffic congestion, etc. We need to bring all of those data sets into a single place and then prepare the data, essentially enrich, contextualize, build more meaningful data out of those discrete data points that we have from customer records, from transactions, from other services. We bring them and then we need to prepare them at scale. At scale is not within a notebook on a CSV file. A scale requires distributed systems that can work with lots of data. Once we prepare the data, we need to build training machines that will take this prepared data, this feature set or feature vectors, and run and try and predict, create a model that knows how to predict the outcomes after looking at some new data. So those training algorithms may run distributed across various frameworks, different algorithms, different, you know, deep learning, machine learning, and they may use different parameters. So we want to compare the same model using different parameters to see which one yields the best accuracy. And finally, we deploy those models into a production system. In the production system, one of the main challenges is how do you bring the production system data in real time, low latency, that resembles or identical to the data that we use for training, because otherwise the model will not work. And then we also need to run all sorts of maintenance and operation aspects on that data. For example, we need to detect if there is a drift in our model, and maybe we need to retrain or refresh the data or create ensembles or other forms of mechanisms that allow us to improve the accuracy over time. Because it's well known that once you have a model, this model will not last for forever. Customer behavior has changed, and with that also data patterns, and data patterns meaning also the model accuracy will change. So we have to have essentially a feedback loop. Now, building those production pipelines is extremely tough challenge. This is where 85 or 80% of the users or the enterprises fail, according to most analysts, Gartner and others, because this is where the paradigms that you have in the research of a data scientist working against small data sets versus what you have in production, which is streaming data and ETLs and operational stuff that need to run 24/7, they're quite different. And you're essentially building everything from scratch. In some cases, recoding things that were done in Python, in data science code, into Java or C to get a decent performance or scale. Moving from, again, sort of Python and pandas to Spark and recoding all your pipelines. And this is also different teams. You're moving from just a single data science or a few data scientists to data engineers and machine learning engineers and software developers and MLOps and all of those things. So the question is really how to do this transition in a way that's least painful and is fastest and require least amount of resources. If we dive deeper into what it needs to happen when we're moving some things what we've done into production, we have to follow all those different steps, anywhere from taking the data science code or the data engineering code, package it in microservices and containers, scale it out using various approaches through load balancing or data partitioning. We have to apply performance or tuning through parallelism, through integration with GPUs, through caching of data, all sorts of techniques that allow us to make our model more performant and this way use less resources, as well as meet the SLA of a real application. When we go into production, we have to think about monitoring, logging, versioning, auditing, security, because everything we take decision on may be used against us. We could be sued because our model is inaccurate or it's creating some gender bias. So everything we do have to be logged and monitored. Also for operational purposes, so we know that right now things are not performing as well. So monitoring will require us to instrument our code and prepare it to be production ready. And finally, we want to make automated workflows that we don't invest too much energy every time we change something. This is where technologies like CI/CDs and automated workflows and rolling upgrades and canaries are coming into play, and they allow us to automate the workflow of deploying software and machine learning into production. So usually the challenge is that while the first step of developing a model, especially today where things are more well understood and there are automation tools to pick features and things like that, it could take weeks to build a model based on existing frameworks. But it could take months and months of many different team members for engineering, data scientists, etc., to build this into production. In some organization, we've seen that takes about 12 to 18 months. And what we're trying to do is essentially cut all this overhead by automating all those different discrete steps that you're seeing here and creating a much more automated flow. So people can deploy something that they've done within weeks and not months or more than a year. So essentially think of a flow where you collect data using all sorts of microservices from streaming sources, ETL sources, etc. Then you're running preparation at scale, you're running training, again, at scale in a distributed fashion, and then you create some artifacts that run in production and are deployed wherever needed, whether it's on premises or in the cloud or as part of a bigger application. And all of that is also leveraging some sort of a data fabric, real-time data fabric that allows us to move things around really fast between those steps. So essentially, if we look at the machine learning pipeline, that's how it looks like in a generalized form. So we have ingestion, which is essentially bringing data from all those discrete and various sources, ETL, streaming, logs, scraping. We need to bring that into some sort of a pile. Later, we need to prepare that data and then contextualize it and build feature vectors. We may run various training algorithms against that data to choose the best performing algorithm. We validate what we've done, what we've trained on And then we finally deploy that. We deploy the model, but we also have to deploy some APIs that go along with it and build this feature vector. And we have to collect matrix for everything that we deploy. So the solution must coexist with 3 different layers. So the first layer has to be data. And this is where Dell, together with Iguazio, provides several solutions that I'll discuss. The second layer is how do we create all those functions, discrete functions, and daisy chain them into high performance pipeline and scalable pipeline with minimal amount of work. This is where we're bringing a technology which is serverless and can run very complex, very high performance workload with minimal efforts, and also utilize library functions for those discrete steps. And on top of it, you should have some automation layer to build those full pipelines and monitor them and orchestrate them. So this is essentially how you build an automated machine learning pipeline, by having those 3 steps, do it yourself or leverage existing frameworks. And essentially what we're seeing is that the world is moving from this approach which is essentially very BI or data engineering oriented, of using Hadoop and potentially Spark in a proprietary software stack of like HDFS, and then scheduling framework called Yarn, which is sort of starting to become out of date, and then a middleware, which also some of it is already long gone, like MapReduce. And instead of having sort of a single siloed approach, and which doesn't deal with data science, doesn't deal with other major microservices, we're seeing the trend to move into more cloud-oriented architecture, where on one end you have managed storage and databases. And this is here where you have assets from both Dell and Iguazio. Iguazio has sort of managed databases, and Dell brings a lot of different solutions for managed storage, Isilon, ECS, and other products. Kubernetes is sort of essentially already conquered the place of becoming the universal scheduler and orchestrator for any workload, not just big data workloads, but big data workloads, data science workloads, deep learning workloads, and various other microservices. And then on top of it, you build your business logic. So this way you essentially reduce the amount of efforts, and you future-proof your architecture to work in the cloud or on premises. This is also if we're looking into Kubernetes. So Dell and VMware have solutions like VMware Tanzo, or you could use any other Kubernetes framework. So again, if we're zooming into the solution that we've worked with and together with Dell, is you have a data layer. The data layer usually comprises of sort of big data files and things like that, like using Dell Isilon or Dell ECS object store. Iguazio provides a very high-speed real-time database that is very unique. It's designed specifically to do high-speed analytics and machine learning, and it's sort of essentially tying all those microservices together. Then you have a layer of Kubernetes running on top that orchestrates the different workloads. What we're delivering is a set of managed functions and services. Managed services, pretty much like in the cloud. When you go to Amazon and you want sort of big data service, you can just go and use EMR. Or you want SQL as a service, you go and use Athena. Or use serverless functions, you go and use Lambda or DynamoDB for database, etc. So Iguazio have the equivalent solutions. It's just the main difference. It's multi-cloud, and it's based on open source components. Some of them we've contributed to the industry, like Nucleo and MLRun and a bunch of others. Some of them we've adopted the best-in-class technology and made it more of a managed service than just install and roll your own. Managed service meaning security, meaning elasticity, manageability, all of those things are baked in. So you use the open source, but you don't have to pay the technical depth of adopting and integrating it. On top of it, you have a layer of pipeline orchestration for the various tasks in machine learning. So AutoML, experiment tracking, data lineage tracking, feature stores, workflow management, leveraging an engine, open source engine called Kubeflow. So this way you have sort of a full stack, which is pretty much like a managed cloud service, just runs everywhere, on premises or in the cloud. So just as a glimpse of it, you can see that you have solutions part of the platform. It's, again, fully integrated. You have Elastic Notebooks, and you have managed pipelines that you can essentially assemble those workflows of training, data preparation, deployment, etc. I'll show a demo in a minute how you build that. Everything that you're doing is automatically tracked using artifact management and experiment tracking. All of that is fully automated. And then you can manage the entire set of services, what kind of CPU, memory usage, GPU usage per user, per application, per project, etc. You can go and provision new services like Spark or machine learning services just through a wizard. So again, you have a full stack of service management, pretty much like a cloud solution. One of the main things that we've done, which is also open source, is building on the concept of serverless function. If any one of you heard like Amazon Lambda, just taking it to a different place. Iguazio, including myself, are coming sort of a lot from high performance background. So we've essentially built a very high performance serverless engine. And what makes make it very powerful, because when you process data, you cannot just rely on something which is single threaded or slow performing like Lambda. You need something that can essentially do stream processing, can work against stateful data, etc., which is quite different than other serverless frameworks. So we've designed solutions like Nucleo and others which are open source, so someone can just go and take the same Python code or same Java or Go code and run significantly faster, same code without modifying it. This is an example. There's also a blog in Towards Data Science showing how you can take something that runs in like 20 megabytes per second throughput, and with just running it within the Nucleo framework, it runs at 500 megabytes per second. So 20, 30 times faster without changing your code. So that means you don't need to essentially recode your solution into production artifacts. Other aspect, it automatically deals with auto scaling. Remember, one of the challenges is how do you scale your workload to handle more and more requests. So not only it's extremely fast, it also auto scaling. It brings logging, monitoring, versioning, security all out of the box. So it essentially instruments your code automatically. And we have customers that essentially manage to build projects using this approach within weeks and productize them because they only focus on the business logic. Other interesting aspects is once you have those concepts of managed functions, you can just daisy chain them and create pipelines. So if you want to do something like data preparation and then training and deployment, feature analysis, whatever, you have pre-baked functions which are also reusable. You can write them and reuse them in multiple projects, or you can actually take 50 functions that we already baked for you that introduce AutoML functionality and NLP functionality and deep learning functionality and data engineering functionality, etc. You could just take those and use them as part of your pipeline. So together with Dell, we essentially not only developed technology, which I'll demonstrate in a minute, we also did a lot of testing. We had a large team with the Dell and Iguazio that essentially built reference architectures with hardware, with software, with everything. And so you guys can focus on just doing the work, and you can get something pre-installed with, you don't even have to go to us to buy it. You can just go to Dell and get a software SKU, which adds the software on top of the hardware. And there are a lot of interesting use cases from customers that show significant ROI for the solution and cutting time to deployment, cutting performance significant. And I'll show some of those use cases in a minute. Okay, so let's move into some of the use cases. So this is an example of an application that's a hospital. It's essentially, today healthcare is something very important and also very sensitive. So think about hospitals where they need to build hybrid solution where the medical records of patients are in a hospital, and you need to essentially go and collect that data and analyze it, provide some way for the analysts within the hospital to see how different diseases, like COVID or others, spread and behaviors, and analyze all sorts of things that will help them with actually creating some proactive treatment approaches. But you can also build real-time dashboards that react, they collect vitals from patients, heartbeats and temperature and all the other things, and create real-time data as well as predictions. And I'll show you in the next screen, essentially is a screen that's used in ICU for analyzing patient care. So you can build those solutions on premises. You can connect to sort of an online data lake, for example, install like Isilon or something like that, and connect Iguazio systems to it. And also you can just go and anonymize the data and push it into the cloud and run second part of the system for research or model training or other things, or essentially bursting your computing into the cloud on Azure. So this way you can build hybrid solutions that on one end have a piece on premises, in the hospital, on another, they're also in the cloud. Essentially, if you go zoom into one of the use cases in this hospital, which is one of the leading hospital and also pretty dominant in the COVID research, essentially you think about all the information from ICU can feed into the system, including even images, because people know that today you can deduct a lot of information from images using some simple deep learning analysis. So all the information about patient care, admission, vitals, images, etc., flows into one system. This system analyzes all the data by using those multiple steps that I mentioned, and it generates essentially events triggers for doctors. It can generate dashboards that shows you a prediction of what needs to be done for every patient, and who has a bigger likelihood to survive, and all those things, and all the data is also anonymized. And it could also do push notifications to mobile applications. So you could build something very interesting like that with very little amount of work. Other use case is around fraud prevention. We have one of the customers, one of the unicorns in the payment system. Essentially want to move from detecting fraud to identifying fraud and preventing it in real time. And doing AI in real time is more and more complicated because you have to bring data which is always up to date. Because someone doing a fraudulent transaction, you have to learn that information immediately and respond within seconds. So the second thing that they wanted to do is cut the time to production from 3-4 months development time and release cycle. They want to move to something which is continuous. You have a bug, you solve it, you deploy. You introduce a new feature, you improve your accuracy, you do it immediately. You don't have to wait 3 months for a version. So the original architecture is very sort of a Hadoop big data oriented. You have your database, you run ETL jobs to extract some data. You form feature vectors by using SQL commands. And then you're doing some batch prediction and responding back into the system. So that process has inherent 40 minutes delay. So that means that if someone is starting to make a fraud and steal money, then you're essentially not going to see that, because within 10 minutes, he already took all the money. You can only chase him with lawyers, and that's pretty expensive. So what you want to do is do everything in more of a streaming fashion, which is like this. So essentially every transaction that happens in the database feeds into a real-time system. You have functions that essentially form those real-time feature vectors. They store it in this real-time feature store. Some features are generated in a more aggregate way across bigger time windows. So you form here all the data required for training. Training will be invoked regularly to keep the model up to date and generate the model. And then every time there is an event, there is an inferencing function that is getting called with the up-to-date feature vector, which include aggregations of all the previous transactions, when was doing this kind of transaction before, going to a certain merchant versus other merchant. There are all sorts of statistics generated here. And once it's getting the transaction, it immediately takes a decision to block the account. So this function here writes directly into the database, into the user record. It's essentially going and saying this account is blocked. So this entire process takes about 12 seconds from the first indication of fraud until the customer account is blocked due to that fraud. So moving it from 40 minutes. So it's a huge difference. Now it means that this company top line is much higher because they're not losing money. We actually have seen that the total ROI for the hardware and software for the entire system, which was purchased for like 3 years in advance, TCO, then within weeks, they already recouped the entire investment because now they stopped losing money due to fraud, and they can also go into new businesses which are more risky because they're not so afraid of being exposed to risk. The other aspect here that everything here is a managed microservice that has its own life cycle. You can just change the code, upload it to production with an automated flow that takes a few minutes. So that's it. Then you don't have to wait 3-4 months for a version. Now, if we're taking another use case of more predictive maintenance, we see that pipelines are not so simple. If you need to take into account the development pipelines as well as the operation pipelines, this is an example of another project we have of predictive maintenance. So you have to stream data from like Kafka streams or operational databases. You have raw data, you need to process it. You need to build the features. Out of those features, you need to go and do additional analysis to select the most interesting features. And then you run the training and validation and create models. But this is just the first step. This is just the development. Once you've done the development, then you need to take those models and serve them in a real application and together with APIs. And those functions actually need data. Where do they take data from? So you need some real-time access to those feature sets. And then everything that's done is also going to be tracked. So we want to measure if we have issues around performance of the models, around losing accuracy of the models. So there are other machine learning functions that essentially analyze the serving function to identify drift, and they can visualize it. And based on that analysis, they can also re-trigger upgrades of the model. So this is really the holy grail. Doing that on our platform, it's a matter of weeks, and anyone who wants to see a demo, I'm more than happy to show that. So essentially, the real value is taking a process that has so many steps of manual work and projects that will end up in 12 months. So you can essentially shrink it to something which takes weeks. The development and the deployment, and you could also repeat the deployment over and over within every few weeks. So it's also a repetitive case, and also this is again automated and runs in the cloud or on premises. So you have future proof. You want to use it on premises because this is where your data, but you want to be able to scale to the cloud, or you find out that the cloud is too expensive. We also have a bunch of customers like that actually ended up in Amazon. They saw that their bill was extremely high because you're getting charged billed on sort of everything. And then they essentially moved to a fixed set of resources and servers. And so their bill starting to shrink. So that's some of the advantages. And again, you can say, you know what, I figured it out. We can just go and build everything ourselves. I don't want you guys to end up like this guy in the picture. It's very complicated. You need someone to give you something that's working and managed. And this is where we, together with Dell, come into the play. So just after, I'm going to show you now some demo. But one of the things that we want as an outcome of this session also, we can bring our data scientists and teams. And if you have some challenges, we can go and do design sessions. And even if you don't buy, and again, a lot of our technologies are open source. We're more than happy of people use them as is. We can go together with our data science team and help you make this transition to turn your work into something which is more operational. So with that, let me just show you a few slides. I don't know how much time we have, but let me try and do sort of a quick demo.
Yep. Hey, this is Anu from Dell.
Yep.
Yeah, I just wanted to add one more point to your own speech. If you want more info about the reference architecture or what Dell and Iguazio has been doing together, you can look for a white paper that was published, and there is a website as well called infohub.delltechnologies.com. You can search for Iguazio there, and you will find tons of resources.
Sure. So quick view into our system. When you log in, again, there's a lot of tutorials, but think of it as sort of a cloud. Again, everyone logs in, everyone has an identity. Yeah, so many managed services that you can choose from to manage the data and the databases, to explore data and create machine learning workflows, to run and manage is real-time functions, to form new services. Let's assume you just want to create a new service. You can go into a services screen and see these are all the services that I'm currently using in my account. So, traditional big data services, machine learning services, operational services. Let's assume I want to run a new service like Spark. It's as easy as choosing Spark, giving it like credentials, resources, and clicking OK. And that's it, sort of number of replicas to start with, and you have a service up and running. So even your own users can do it if they have the right permissions. There is a very strong set of security policies built into it to control exactly what everyone can do in terms of data access, provisioning services, etc. And again, you can see there are so many services here. One of the services is a managed development environment based on Jupyter. We're also adding other development environments based on VS Code and others, and we support PyCharm remote. So someone can just go and develop on the platform, essentially with direct access to all the data and all the computation resources. Instead of using a lot of computation on different desktops and workstation, you could just essentially use an Elastic cluster and submit jobs within this Elastic cluster. So this way, again, you can just go and write some functions in your notebooks, and those functions will automatically be able to transition to a microservice. I just write this Python function, and in a single command, I can essentially go and turn this into a service. But before I'm turning it into a service, I can just go and run it locally on my notebook. I'm just saying run. And this functionality, which in this case is generating and analyzing data, I can just run this functionality on my notebook. And also it records automatically everything I did. At a certain point, I just want to turn my code into a microservice, into a real-time function that runs in production. I have to do a lot of work. I just need to say code to function, which essentially turns my code in my notebook into a running microservice on my Kubernetes cluster. Another nice thing is, as I mentioned, there's a notion of libraries and built-in functions. So let's assume I have a data set and now I want to analyze my data set. I can just pull from a marketplace, I could pull a new function called describe, which analyzes all my data set. I can document my function to see how it works. And then I could just go and run this analysis. I'm just running this function that was imported on my system with the data that I generated internally. So this function will essentially distribute itself to the cluster. So it scales out. It's dynamically allocating resources, which means that it's not going to waste energy when it's not really running, and run an analysis and generate results. So if I want to see the results, essentially the results, because it's a distributed cluster, will essentially end up in my own notebook. I can go and see the result of the analysis of my data coming back into my notebook. There's also like other charts. It's doing all this analysis, so I know which data is more important, etc. And that's without even leaving my notebook. I'm using an Elastic cluster, just submitting stuff into it. At a certain point, I want to build complete pipelines. So I need training functions, I need validation functions, all those different functions that I mentioned. Now, all those, again, you have pre-baked version and you can build your own, but you have pre-baked library functions for all this pipeline. And I could just go and define a pipeline, meaning I run the ingestion and then run the analysis and then run the training. Just like the drawing that I was mentioning, I'm just essentially wiring up those functions in a relatively simple description, saying that, the training takes the data from the ingestion. And for example, my testing is taking the data from the model from the training and the data from the training. etc. And this function is essentially deploying my model. So once I finish running this workflow, I'm essentially going to have a full-blown pipeline. So by having just creating a graph of computation, I created a full-blown production pipeline, and I could actually see the results of each step of the pipeline, obtaining the data, running the analysis on the data with all those charts, running the training on the data with, again, all the results from my training. This is, by the way, using Kubeflow, which is an open source project initiated originally by Google for creating machine learning pipelines. And I can even deploy my model, and finally even validate the performance of my model and the latency of my model. I can also see that in a richer API. Everything that I'm running is essentially being tracked automatically. I don't have to write too much code. I can go, for example, into the training function. I could see which machine it ran and what were all the parameters, what were all the results, who ran it, what was the code that was used in order to run it, what was the data used in that, what are the results, again, of my training functions, again.
Ron, we're 4 minutes past the top of the hour. For those attendees that are still connected, we didn't have any questions that came across, but what if a customer has already started down this journey, never got into production, but they've made a big investment, they have a big data lake, they've got a lot of tools that they've accumulated. What would be your answer to them? How can they take advantage of Iguazio in that case?
So we have many customers that we essentially are transitioning from Hadoop to more of a cloud native architecture, because people sort of get the feeling that Hadoop is not really going anywhere, but on the other hand, they have sometimes petabytes of data running on Hadoop and a huge investment in servers. So there is both can essentially coexist. You can essentially run Hadoop and run the computation side with all those elastic frameworks and machine learning and data science against data that's running on your external Hadoop. And we have customers doing that and also practices how to do that. Maybe gradually they would like to move to more efficient storage like Dell Isilon or ECS when they're starting to do a refresh cycle, but we know how to coexist very well with existing Hadoop solutions. Also with any other databases, we have partnerships with many other database providers, MongoDB and Snowflakes and others that we can plug into their systems, Oracle, Teradata.
That's good to know. Okay, well, I think we're going to have to close it down at this point since we're past the top of the hour. I don't see any other questions at this point. Very good demo. Appreciate it.
Welcome. Thanks.